Throughout human history, the concept of time travel has captivated the imagination. From ancient myths to modern science fiction, the idea of venturing through the past and future has intrigued minds and sparked countless stories. Our time exploration started in the early 20th century with a man named Albert Einstein and his groundbreaking theory of special relativity. This revolutionary concept states that time isn't a constant, unchanging entity. Instead, it's a flexible fabric, interlaced with space in a four-dimensional tapestry known as spacetime. Albert Einstein published his special theory of relativity in 1905, fundamentally changing our understanding of space and time. This theory brings us to a remarkable phenomenon called time dilation. It's a concept that sounds straight out of a sci-fi novel, but it's grounded in solid physics. Here's the gist. As you move faster, time slows down. So, if you were to embark on a journey at near-light speeds, time would tick slower for you compared to someone stationary. You might be wondering, is this just jargon, or is there any proof? Well, let's hear from Neil deGrasse Tyson, an astrophysicist who can shed light on this.
Indeed, there's concrete evidence supporting time dilation. Atomic clock experiments carried out in the 70s, for instance, showed that time indeed passed slower for a clock moving at high speeds compared to a stationary one. These experiments took us a step closer to the fantastical concept of time travel. So in theory, we have our first method of time travel, moving incredibly fast. But there is a problem with that too. Achieving near-light speeds is currently beyond our technological reach. The energy required to propel a spaceship to near-light speed would be too astronomical that even converting the entire mass of Jupiter into energy, it would still be not possible. Einstein's equation, one of the most famous equations in physics, E equals to mc squared, explains this very well. In this case, E is energy, m is the mass, and c is the speed of light. This equation shows the equivalence of mass and energy, and it shows that according to our current understanding of physics, it is theoretically impossible for any object with mass to reach the speed of light. It basically states that as an object accelerates, its relativistic mass increases, which means it gets heavier in a sense that it requires more force to accelerate it further. The closer an object's speed gets to c, the speed of light, the more its relativistic mass increases, leading to an exponential increase in the energy required to continue accelerating it. According to the principles of relativity, the energy required to accelerate an object can be expressed by modifying the previous equation to account for the object's velocity, v relative to the speed of light. This modification introduces the concept of relativistic mass and results in the equation for relativistic energy, which is E equals mc squared over the square root of 1 minus the velocity squared over c squared. This equation shows that as v approaches c, the denominator approaches 0, making the energy E approach infinity. This means that to accelerate an object with mass to the speed of light, you would need infinite energy, which is impossible to provide. This is why, under our current understanding of physics, only massless particles like photons can travel at the speed of light.
Einstein wasn't done altering our perception of time. Later in 1915, he introduced the general theory of relativity, adding another layer to the time travel puzzle. This theory fundamentally changed our understanding of gravity from a force that acts at a distance, as described by Isaac Newton, to a curvature of space-time caused by mass and energy. This theory also suggested that not only does speed affect time, but so does gravity. In fact, the more massive an object, the stronger its gravitational pull, and the slower time passes near it. Imagine standing near a massive black hole where the gravitational pull is so strong that it bends not just space, but time itself. Here, time would crawl to a near halt, making seconds appear as hours, hours as days, and days as years to an observer far away from the gravitational field. This is what physicists call gravitational time dilation. To illustrate this phenomenon, let's turn to the world of cinema. The blockbuster film Interstellar paints a clear picture of gravitational time dilation. In one of the film's most memorable scenes, the characters land on a planet near a black hole, where an hour on the planet's surface equals 7 years outside its gravitational influence. But this isn't just Hollywood magic. It's a principle grounded in real physics. One of the most fascinating consequences of general relativity is the prediction that time passes at different rates in different gravitational potentials, a phenomenon known as gravitational time dilation. The equation describing this effect, for a weak gravitational field in slow movement relative to the speed of light, can be simplified to T prime equals T times the square root of 1 minus 2 gm over RC squared, where T prime is the time interval, measured by an observer at a distance, r from a mass, m. T is the time interval measured by an observer far from the mass, where gravitational effects are negligible. G is the gravitational constant. M is the mass creating the gravitational field. R is the radial coordinate, essentially the distance from the mass. And C is the speed of light. This equation indicates that closer to a massive object, or in a stronger gravitational field, time passes more slowly compared to a position further away. This effect has been confirmed by numerous experiments and has practical applications in technologies like GPS, where the clocks in satellites experience less gravitational pull and thus run slightly faster than clocks on the Earth's surface, requiring adjustments to account for the difference. Thus, gravity gives us our second potential time travel mechanism, but it comes with its own set of challenges. For one, we'd need to find a black hole or similarly massive object. Then we'd have to develop a means of surviving the immense gravitational forces near such an object, not to mention the journey there and back. And even if we could manage all this, we'd still face the issue of one-way travel. As it currently stands, gravitational time dilation would allow us to travel into the future. But returning to our own time would remain a challenge. But what if we could create shortcuts through space and time? Stay tuned as we delve into the world of wormholes, cosmic strings, and quantum entanglement in our quest to unravel the mysteries of time travel. Wormholes, bridges through space-time, offer a possibility for instantaneous travel. These fascinating concepts emerge from the equations of Albert Einstein's general theory of relativity, though no empirical evidence has yet confirmed their existence. In essence, a wormhole would be like a tunnel with two ends, each at different points in space and time. Regarding time travel, wormholes introduce intriguing possibilities. If one end of a wormhole could be accelerated to a significant fraction of the speed of light and then brought back to its original location, a scenario inspired by the twin paradox and special relativity, time dilation could result in the two ends of the wormhole being at different times. This effect is a consequence of general relativity, which allows for the possibility that moving clocks run slower relative to stationary ones. Hence, a wormhole could potentially allow for travel not just across space, but also time, effectively becoming a time machine. This theoretical form of time travel through wormholes would not only allow for travel into the future, which is directly predicted by general relativity through time dilation effects, but might also allow for the possibility of travel into the past. However, The concept of traveling back in time raises complex paradoxes, most famously the grandfather paradox, where a time traveler could potentially prevent their own existence by altering past events. The existence and stability of wormholes for human use involve significant challenges. According to theoretical physics, keeping a wormhole open would require a form of matter with negative energy density, so-called exotic matter. To date, such material has not been found, and the creation and maintenance of a stable wormhole for time travel remain speculative concepts within the realm of theoretical physics. Despite the exciting possibilities they represent, wormholes and their implications for time travel are still largely theoretical and face numerous scientific and technical hurdles. Wormholes could provide cosmic shortcuts, but could the universe itself hold the key to time travel? Born from the Big Bang itself, cosmic strings might offer a route back in time. These peculiar entities are not your typical strings. They are, in fact, incredibly dense, thinner than an atom, and potentially stretching across the whole universe. These are cosmic strings, the defects in the fabric of space-time, birthed in the chaos of the universe's inception. Now you might be wondering, how do these cosmic strings relate to time travel? The intense gravitational field around a cosmic string would produce a strong gravitational potential. This, according to general relativity, would result in time dilation, where time moves slower in a strong gravitational potential. And if two such strings were to move parallel to each other, they would create a space-time geometry in which their combined gravitational pull might significantly distort space-time. It is theorized that the space between them would be warped in such a way that it could create a closed time-like curve, CTC. A CTC is a trajectory in space-time that loops back on itself, effectively allowing a path from the future to the past and potentially enabling time travel, at least in the mathematical sense. It's a captivating idea that's been discussed in depth in scientific circles, including a notable paper published in Nature Physics in 2005. However, as fascinating as this concept is, it's not without its challenges. For starters, we've yet to directly observe these cosmic strings. Plus, near a black hole or cosmic string, the gravitational forces would be immense. They would stretch and squeeze anything nearby, including our hypothetical time traveler, into a thin strand of atoms, a process unceremoniously known as spaghettification. For journeys like these, we would need to develop materials and structures that can withstand extreme distortions. Then there's the question of energy. How much would we need to manipulate these strings? And of course, the ever-present issue of paradoxes. What happens if you alter the past? Time travel, especially to the past, opens up a whole can of worms. Take the infamous grandfather paradox, for example. If a person were to travel back in time and accidentally cause their grandfather's premature demise, they would then never have been born to travel back in time in the first place. It's a cyclical mystery that could potentially untwist the very fabric of reality. Paradoxes like these challenge our understanding of causality and question the nature of reality itself. Some physicists propose the existence of parallel universes to resolve these paradoxes, but this is still a highly debated topic. In summary, the search for time travel entails an adventure through the boundaries of human comprehension and the structure of space-time itself. It pushes the limits of our scientific understanding, alters our senses, and dares us to imagine possibilities beyond what is currently possible. Time travel remains a fascinating mystery, for the time being due to its practicalities and paradoxes. As we continue to explore the universe and push the limits of our technology, perhaps one day we will unlock the secrets of time travel. Until then, It serves as a profound reminder of our place in the cosmos and the endless quest for knowledge that defines our species. If you enjoyed this journey through the captivating realms of time travel and the mysteries of the universe, don't forget to like, comment, and subscribe for more adventures on our science cruiser.